Let's take a look at our first example. It says Raul has taken 2 tests in his chemistry class. He scored a 72 on the first test, for which the mean of all scores was a 65, and the standard deviation was an 8. And he received a 60 on the second test, for which the mean of all scores was a 45, and the standard deviations was a 12. So here's the issue. If we look at the individual scores of the test, we have a score of a 72, and we have a score of a 60. If I said, which test did he do better on, almost all students would say, well, clearly he did better on the first test. He did better on the first test because his score is higher than the second test. Well, that's not necessarily true, and it's most definitely not true if you're in a class where they curve the tests. What we're asking in this one is not how did he do compared to himself, which of those 2 tests did he better in. We're saying, how did he do compared to the rest of the students in the class? So how do you compare one score to everyone else? Not to itself. How do you compare one score to everyone else? You're always going to use z-scores. So what do we have here? We have 2 different tests we need to look at. We have the first test and we have the second test. Okay. What do you always need to know? You always need to know the data value, and you always need to know the mean, and you always need to know the standard deviation. So the data value, the mean, and the standard deviation. So let's go ahead and read through this and see if we can figure out what it was. On the first test, he scored a 72. So that's our data value. The mean of all of it was 65. Great. And then the standard deviation was an 8. Excellent. Second test, he received a 60. So that's our data value. The mean was a 45. Okay. And the standard deviation was a 12. Got it. So there it is for the information that I need. Now what I want to do is I want to calculate the z-scores. So what was the z-score when he scored a 72? Well, you do the data, 72, minus the mean, 65, divided by the standard deviation, which is 8. Likewise on test 2, to find the z-score of when he scored a 60 on the exam, you're going to do the data, which is 60, minus the mean, 45, over the standard deviation, which is 12. So go ahead and calculate those z-scores right now. I'm going to go ahead and write them as decimals. I'm getting 0.875 for the first test, and I'm getting 1.25 for the second test. So these are my 2 z-scores. The question is which one did he do better on? Well, on the first test, he physically scored higher than the second test. A 72 is better than a 60. I agree with that. But that's not what this question is. The question is, how did he do compared to everyone else? Well, think about that mean. That mean is a 65 for the first test, and he scored above with a z-score of, so he scored 0.875 standard deviations above the mean. Look at test 2. Yeah, he only scored a 60, but the mean was really low. It was a 45. So his z-score on that one was a 1.25. That would be further to the right than a z-score of 0.875. So if you're a visual person, let me kind of show you what's going on here. What you have here is the mean, and you have the data scores. I'm going to draw them like this, and this is where it's at right here, okay? So on the first one, again, you had a mean of 65, and then you have the majority of people again have to be between 1 standard deviation of the mean. Well, where was he? He was just below 1 standard deviation above the mean. That was the 0.875 part, right? Whereas let's look at this second one. Let's do that 1 standard deviation above and below the mean again. He was actually further to the right at 1.25 standard deviations above the mean. So in the green one, in the second test, he scored higher than all of those people, whereas in the pink one, the first test, he only scored higher than this many people. So the idea is he scored higher than more people on the second test than he did on the first test because he has a higher z-score. So with test scores, well, I mean, I guess it depends on what the test is, but on this test score in a chemistry class, you're looking for when did I do better than most of the students in the class? The answer would be test 2. Test 2 has the higher z-score, and I'm looking for the higher z-score in this example. Let's go on to the next example. Let's go on to example 2. So example 2 says, Cheryl has taken 2 quizzes in her history class. She scored 15 on the first quiz, for which a mean of all scores was 12 and a standard deviation was 2.4. Her score on the second quiz, for which a mean of all scores was 11 and the standard deviation was 2, was 14 in comparison to her classmates. Did Cheryl do better on the first quiz or the second quiz? Again, so the first quiz she scored a 15, on the second quiz she scored a 14. So if you just went by the score, you would say she did better on the first quiz. However, that's not what the question is. The question is not which one did she do better on compared to herself, which one did she do better on compared to everyone else. So doing better means we want to be further to the right. We want more people below us. So again, we're looking for the higher of the z-scores. So what we're going to do here is we're going to calculate the z-score for both of these tests or both of these quizzes, and we're going to pick the one that has the higher z-score. So let's give this a shot. Look at quiz 1, look at quiz 2. You need to be able to identify the data value, you want to identify the mean, and you want to identify the standard deviation for both of these quizzes. The data value, the mean, and the standard deviation for both of these. Let's read through this and see if we can do it. It says she scored 15, so that's her data value on the first quiz, for which the mean of all scores was 12, so the mean is 12, and the standard deviation was 2.4. Great. Let's go on to the second one. Her score on the second quiz, for which the mean of all scores was 11, so the mean was 11, standard deviation was 2.0, okay, and her score was a 14. So now let's calculate the z-score. The z-score for the 15, when she got a 15, is the data, 15, minus the mean, 12, divided by the standard deviation, 2.4. The z-score for 14 is the data, 14, minus the mean, 11, divided by the standard deviation, 2.0, or just 2. Go ahead and put those into your calculator. Let's see what you get. For the first one, I'm getting a z-score of 1.25. For the second quiz, I'm getting a z-score of 1.5. Again, 1.25 means I'm 1 1/4 standard deviations to the right of the mean. 1.5 means I'm 1 1/2 standard deviations to the right of the mean. The goal would be to be further to the right. So the z-score of 1.5 would be the highest. That means quiz 2 would be the quiz that she did better on, not the score, compared to everyone else. Quiz 1 she got a better score on. Quiz 2 she did better on compared to everyone else. So I hope that makes sense to you as to what the z-score is in this case. It is just relative position. It is not your individual score. It's how'd you do compared to everyone else. Okay? It says the z-score equation, z of x equals x minus x bar over s. So that's data minus mean over standard deviation, involve 4 variables. So you've been calculating the z-scores. But the idea is if I give you 3 of those 4 things, the data, the mean, the standard deviation, and the z-score, if I give you 3 of those 4 variables, you should be able to find the 4th variable. So that's going to be illustrated in the next example. Let's look at this one. It says a consumer group tested a sample of 100 light bulbs. It found that the mean life expectancy of the bulbs was 842 hours, with a standard deviation of 90. One particular light bulb from Durabright Company had a z-score of 1.2. What was the lifespan of the bulb? So on these problems, we have 4 things that we're looking at. The data, the mean, the standard deviation, and the z-score. So we have to go through those and think, which one of those do we need? And remember, the formula is, the z-score is the data minus the mean over the standard deviation. So we're going to plug it into that formula once we get our numbers. So let's read this. It says the mean life expectancy was 842 hours. So the mean is 842. It says our standard deviation was 90. Great. Standard deviation 90. And then it says the z-score was 1.2. So the z-score was 1.2. And it says, what is the lifespan of the bulb? In other words, it wants to solve for x. So let's go ahead and plug this in. The z-score is 1.2, so we're going to have 1.2 equals the data we don't know. So we're going to have x minus the mean. The mean we said was 842, divided by the standard deviation. The standard deviation was 90. Okay? Simple equation here, linear equation that you should be able to solve. We need to solve for x, so to get rid of the divided by 90, I have to multiply both sides by 90. When I do that, the 90s cancel on the right, and I have x minus 842. On the left, I have 90 times 1.2, which is 108. Now I need to add 842 to both sides of the equation. When I do that, I'm getting x equals, well, 108 plus 842 is 950. So how long did this last? It lasted 950 hours. If it had a z-score of 1.2, it lasted 950 hours. So the exact same equation, we have 4 variables. If I give you any 3 of those variables, you should be able to find the 4th variable.